Professor Belfrost's computer science class is back!
Hi, welcome back to my tutorial. And today I'll continue on explaining about my last lesson on input and output module. Okay, so this will be the last lesson that discuss about input output module, and from next lesson we will start discussing about processor and memory. Okay, so prepare for your last lesson on IO module. Let's go. Okay, so computers componentry, yeah, still IO. Okay, so let's review a little about the last lesson, computer component 2. Okay, I've explained before that there are many important terms related to computer systems. So first is computer architecture, which refers to attributes of a system visible to a programmer having a direct impact on the logical execution of program. And also computer organization that refers to operational units and their interconnections that realize the architectural specifications. Also, we have the term structure that refers to the way in which the components are interrelated, and also we have function. Okay, so function refers to the operation of each individual component as part of the structure. Okay, so there are only four function of a computer. So what we will do with computers: data processing, data storage, data movement, and control. And then the third point here is the general structure in von Neumann architecture. Computer consists of a main memory, an ALU, a control unit, and input-output equipment operated by the control unit. And there are five major functions for an I/O module, which is control timing, processor communication, device communication, data buffering, and error detection. And there are three principal I/O techniques which we will discuss in depth for today, in detail for today, which is program I/O, interrupt-driven I/O, and direct memory access. As actually these three techniques actually needs quite a long time to explain, and I'll not explain every point, each point in detail. So I want you to review my video, each slide by yourself after you watching this video. Also find more information in other literatures. Okay, so first, here is the structure of IO module that I've shown you in the last lesson. Okay, so we can see that here in the block diagram, so the module connects to the rest of the computer through a set of signal lines, and data transferred to and from the module are buffered in one or more data registers. You can see in the left side there may also be one or more status registers and maybe also control register. Okay, which one kind of status registers. Also, the logic within the module interacts with the processor via a set of control lines. Okay, you see control lines, the bottom part. Okay, and the processor uses the control lines to issue commands to the I/O module, which is very useful. Okay, some of the control lines will be used for I/O module for updation and status signals. Okay, and the module must also be able to recognize and generate addresses associated with the device's controls. So each of them will be assigned a unique address, okay, or a unique set of addresses. And finally, the I/O module contains a logic specific to the interface with each device that it controls. Okay, and an I/O module that takes on most of the detailed processing burden, presenting a high-level interface to the processor, is usually referred to as I/O channel or I/O processor, whereas an I/O module that is quite primitive and requires detailed control is usually referred to as I/O controller or device controller. So I/O controllers are commonly seen in microcomputers, whereas I/O channels are mostly used on mainframes. Okay, so now we enter the main discussion. There are three techniques for I/O operations. Let's overview once again. First is program I/O, so data are exchanged between the processor and the I/O module, which is good a program that gives it direct control of the I/O operations, including sending the device status and a read or write command and transferring the data. Okay. When the processor issues a command to the I/O module, it must wait until the I/O operation is complete, and if the processor is faster than the IO module, then this is just a waste of time. And this is one of the disadvantages using this operation technique. Okay. The second is that interrupt-driven I/O, which processor issues an I/O command, continues to execute other instruction, and is interrupted by the I/O module when the latter has completed its work. And the third is the DMA. So in DMA, this mode, so I/O module and memory exchange data directly without processor involvement. Okay, so you can just communicate directly. Okay, let's start in-depth discussion. First, with program I/O. So in this mode, when the process is executing a program and encounters an instruction related to I/O, it executes the instruction by issuing a command to the appropriate I/O module. This I/O module will perform the requested action and then set the appropriate bits in the I/O status registers. It takes no further action to alert the processor, so it doesn't interrupt the processor. And the responsibility of the processor periodically to check the status of the I/O module until it finds that operation is complete. Okay, so now let's view from the point of view of the I/O commands issued by the processor to the I/O module, and then from the point of view of the I/O instructions executed by the processor. Okay, first I/O commands. So to execute an I/O related instruction, the processor issues an address specifying the particular I/O module and external device and an I/O command. Therefore, types of I/O commands that an I/O module may receive when it is addressed by a processor. So you have control, test, read, and write. The explanation, read it by yourself just on its own. Very detailed. Next, let me explain I/O instructions. So with program I/O, there's a close correspondence between the I/O related instructions that the processor fetches from memory and the I/O commands that the processor issues to an I/O module to execute the instructions. That is, the instructions are easily mapped into I/O commands, and there is always a simple one-to-one relationship. The form of the instructions depends on the way in which external devices are addressed. Typically, there will be many I/O devices connected through I/O modules to the system, and each device is given a unique identifier or address, as I have stated before. Okay, when the processor issues an I/O command, the command contains the address of the desired device. Thus, each I/O module must interpret the address lines to determine if the command is for itself. And when the processor, memory, and I/O share a common bus, two modes of addressing are possible. First is memory map, and the second is isolated. Let me explain these two modes. Okay, so with memory map I/O, there is a single address space for memory location and I/O devices. So the processor treats the status and data registers of I/O modules as memory locations and uses the same machine instruction to access both memory and I/O devices. With memory map, a single read line and a single write line are needed on the bus. Alternatively, the bus may be equipped with memory read and write plus input and output command lines. Now, the command line specifies whether the address refers to a memory location or an I/O device. The full range of addresses may be available for both. Okay. If we want, we can also make the address space for I/O isolated from that for memory. And this one is called isolated I/O. So isolated I/O is just the evolution of memory map I/O. Now let's us discuss about interrupt-driven I/O. Okay, so from previous explanation, I think I've clearly stated that the problem with program I/O is that the processor has to wait a long time for the I/O module of concern to be ready for either reception or transmission of data, and this while waiting must repeatedly interrogating the status of the I/O module, which is just a waste of performance, right? It's just degradation of the performance. So we have found new alternative for this, and the alternative, the solution is that uh, the processor need to issue an I/O command to a module and then go on to do some other useful works. So the I/O module will then interrupt the processor to request service when it is ready to exchange data with the processor. And the processor then executes the data transfer as before, and that assumes the formal processing. This is the mostly used one, I think, nowadays. And let us consider how this works. Okay, so for input, the I/O module receives a read command from the processor, and the I/O module proceeds to read data in from an associated peripheral device. Once the data are in the modules, data register, the module signals an interrupt to the processor over a controller. The module then waits until data are requested by the processor, and when the request is made, the module places its data on the data bus and is ready for another I/O operation. But from the processor's point of view, the action for input is as follows. The processor issues a write command, it then goes off and does something else. Okay? At the end of each instruction cycle, the processor just checks for interrupts. When an interrupt from the I/O module occurs, then the processor saves the context of the current program and processes the interrupt. In this case, the processor reads the word of the data from the I/O module and stores it in memory. It then restores the context of the program it was working on and resumes execution, which is, in this case, much more efficient, right? Now let's consider the role of the processor in interrupt-driven I/O in more detail. Okay, I want you to view this picture, this scheme, the diagram that I've prepared for you. Okay, so from here, we can see that the occurrence of an interrupt triggers a number of events, both in the processor hardware and in the processor software. When an I/O device completes an I/O operation, the following sequence of hardware events occurs. First, the device issues an interrupt signal to the processor. Second, the processor finishes execution of the current instruction before responding to the interrupt. And then, third, the processor tests for an interrupt, determines that there is one, and send an acknowledgement signal to the device that issued the interrupt. Okay, and fourth, the processor now needs to prepare to transfer control to this interrupt routine. IS and to begin, it needs to save information needed to retrieve the current program, which is interrupted, okay, which is the status of the processor, okay, in a register called the PSW, and also the location of the next instruction to be executed, which is pushed onto the system control stack, okay. The processor now loads the program counter with entry location of the interrupt handling program that will respond to this interrupt. Depending on the computer architecture and operating system design, there may be a single program or one program for each type of interrupt, or maybe one program for each device and each type of interrupt. If there's more than one interrupt handling routine, then the processor must determine which one to involve. Okay? Once the program counter has been loaded, the processor proceeds to the next instruction cycle, which begins with an instruction fetch. Because the instruction fetch is determined by the contents of the program counter, the result is that control is transferred to the interrupt handler program, IHP. And the execution of this program results in the following operation. 6. At this point, the program counter and the PSW related to the interrupted program have been saved on the system stack. However, there is other information that is considered part of the state of the executing program, and all of these values plus any other state information needed to be saved. Typically, the interrupt handler will begin by saving the content of all registers on the stack, and the stack pointer is updated to the point to the new top of stack, and the program counter is updated to point to the beginning of the interrupt service routine, ISR. 7. The interrupt handler next processes the interrupt, and this includes examination of status information relating to the I/O operation or other events that cause an interrupt. 8. When interrupt processing is complete, then the saved register values are retrieved from the stack and restored to the registers. 9. The final act is just to restore the PSW and program counter values from the stack, and as a result, the next instruction to be executed will be from the previously interrupted program. Note that it is important to save all the state information about the interrupted program for later resumption. This is because the interrupt is not a routine call from the program, rather, the interrupt can occur at any time, therefore any point in the execution of a user program. Its occurrence is just basically unpredictable. Okay. So there are two design issues arise in implementing interrupt-driven I/O. The first one is because there will almost invariably be multiple I/O modules. How does the processor determine which device should the interrupt? And the second one is if multiple interrupt have occur, how does the processor decide which one is to process? So first we need the device identification techniques. There are four general categories: multiple interrupt lines, software fault, daisy chain, and bus arbitration. The most straightforward is the first one, multiple interrupt lines. Yeah, you just need to provide multiple interrupt lines, but this is impractical to dedicate more than a few bus lines or processor pins to interrupt lines. Okay, and each line will have multiple I/O module attached to it, and thus maybe we need to consider about using other three techniques for more efficient. So the first alternative is software fault. When the processor detects an interrupt, it branches to an interrupt service routine whose, whose job it is to poll each I/O module to determine which module caused the interrupt. Okay, in this case, the processor will raise the test I/O and places the address of a particular I/O module on the address line. Then the I/O module responds positively if it is set the interrupt. Okay, the processor then reads the status register of each I/O module to identify the interrupting module. Then once the correct module is identified, the processor will go to the device service routine and to specific to that device. But there's one disadvantage using the software port, which is the software port is time consuming. Okay, because it just need to poll every devices. Okay, there are more efficient technique which is called decisioning, which is a hardware port actually. For interrupts, all I/O modules share a common interrupt request line. So the interrupt acknowledge line is daisy chained through the modules. When the processor sends an interrupt, it sends out an interrupt acknowledge. This signal propagates through a series of I/O modules until it gets to the requested module. So the requesting module typically responds by placing a word on a data line, okay, which is called a factor. Okay. In either case, the processor uses the factor as a pointer to the appropriate device service routine. This will avoid the need to execute general interrupt service routine first, and this is called a factor interrupt. Okay. There's another technique which is called uh, bus arbitration. Okay. With bus arbitration, an I/O module must first gain control of the bus before it can raise the interrupt request line. Thus, only one module can raise the line at a time. When the processor detects the interrupt, it responds on the interrupt knowledge line. And requesting it, then it places it factor on the data lines. Okay. Now we are going to DMA. Okay. For interrupt-driven I/O, though more efficient than simple program I/O, it still requires the active intervention of the processor to transfer data between memory and I/O module, and any data transfer must traverse a path through the processor, which is sometimes not needed. So both of these forms, the previous forms, suffer from these drawbacks. The first one, the I/O transfer rate is limited by the speed with which the processor can test and service a device, and the second is the processor is tired in managing an I/O transfer. Okay, when large volume of data to be moved, a more efficient technique may be required, which is DMA. What is a DMA? DMA involves an additional module on the system bus. The DMA module is capable of mimicking the processor and indeed of taking over control of the system from the processor. It needs to do this to transfer data to and from memory over the system bus. For this purpose, the DMA module must use the bus only when the processor does not need it, or it must force the processor to suspend operation temporarily. The latter technique is more common, is referred to as cycle stealing because the DMA module is in fact steals a bus cycle. Okay, so here's DMA block diagram, and let me explain. Okay, so whether a read or write is requested using the read or write control line between the processor and the DMA module. Second, the address of the I/O device involved communicating on the data lines. Third, the starting location in the memory to read from or write to communicated on the data lines and stored by the DMA module in address registers. Fourth, the number of words to be read and written again communicated via the data lines and stored in the data. Uh, The processor then continues with other work. It has delegated this I/O operation to the DMA module, and the DMA module transfers the entire block of data one word at a time directly to or from memory without getting through the processor. When a transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and the end of the transfer. In each case, the processor is suspended just before it needs to use the bus. So the DMA module then transfers one word and returns control to the processor, and note that this is not an interrupt. The processor does not save a context and do something else. Okay? Rather, the processor pauses for one bus cycle, and the overall effect is to cause the processor to execute more slowly. Nevertheless, for a multiple word I/O transfer, DMA is far more efficient than interrupt-driven or programmed I/O. The DMA mechanism can be configured in a variety of ways. There are three ways shown here, as shown in the picture below: a single bus detached DMA, a single bus integrated DMA, I/O, and I/O bus. Let's explain the picture one by one. Okay, so first example, all modules share the same system bus, and the DMA module just acts as a surrogate processor, uses program I/O to exchange data between memory and I/O module through the DMA module. This is inexpensive but inefficient. For the second example, that is a path between the DMA module and one or more I/O modules that doesn't include the system bus. The DMA logic may actually be a part of I/O module, or it may be a separate module that controls one or more I/O modules. Okay, and then from this we can just take one step further by connect the I/O module to the DMA module using an I/O bus, which is shown in the third example. This will reduce the number of I/O interfaces in the DMA module to one and provides for an easily expandable configuration. Nowadays, computer systems are working as explained below. First, the CPU directly controls a peripheral line. This is seen in the simple microprocessor control devices. The second, a control or I/O module is added, then the CPU uses program I/O without interrupts. With this step, the CPU becomes somewhat divorced from the specific details of external device interfaces. Third, the same configuration as in step 2 is used, but now interrupts are employed. The CPU then spend time waiting for an I/O operation to be performed, thus increasing efficiency. Fourth, the I/O module is given direct access to memory via DMA. It can now move a block of data to or from memory without involving the CPU except at the beginning and the end of the transfer. Fifth, the I/O module is enhanced to become a processor in its own right with a specialized instruction set tailored for I/O. 6. The I/O module has a local memory of its own and is in fact the computer is actually indeed a computer in its own right. So with this architecture, a large set of I/O devices can be controlled with minimal CPU involvement. Okay, so uh, a common use for such an architecture has been to control communication with interactive terminals. So the I/O processor takes care of most of the tasks involved in controlling the terminals. I/O module is often referred to as I/O channel for this one. And for the previous example, okay, from the previous point, which allow the CPU to specify a sequence of I/O activities and has to be interrupted only when the entire sequence has been performed, this I/O module is often referred to as I/O channel. Now, let's discuss about I/O channel because we have discussed this in the last 2 points. Okay, what's I/O channel? Not I/O pointer. I/O channel. Okay. So I/O channel represents an extension of the DMA concept, which give ability to execute I/O instruction, which give it complete control over I/O operations. In a computer system with such devices, the CPU doesn't execute I/O instruction. Such instructions are stored in memory to be executed by a special purpose processor in the I/O channel itself. Thus, the CPU initiates an I/O transfer by instructing the I/O channel to execute a program in memory. Then the program will specify the devices, the area or areas of memory for storage, priority, and actions to be taken for certain error conditions. The I/O channel follows this instruction and controls the data transfer. There are mainly two types of I/O channels which is common, which is called selector and multiplexer, as illustrated below. For channel, it controls multiple high-speed devices and at any one time is dedicated to the transfer of data with one of those devices. Thus, the I/O channel selects one device and affects the data transfer. Each device or a small set of devices handled by a controller or I/O module that is much like the I/O modules we have been discussing. Thus, the I/O channel serves in place of the CPU in controlling the I/O controllers. The second is multiplexer channel, which can handle I/O with multiple devices at the same time. So for low-speed devices, a multiplexer accepts, or transmits characters as fast as possible to multiple devices. I'm sorry, my English pronunciation is not very good. Okay. So yeah, that's for the discussion of today, and we have done explaining I/O so far. And next lesson, we'll start discussing about processing CPU. Great. So here are three assignments for you. Don't worry, there are many information that you can get by browsing online. Okay. Okay. The first is to explain this diagram. This is about three types of I/O operations. So I want you to explain actually how each operation works, each technique works. Okay. And the advantages and disadvantages, which is actually quite clear from the diagram. You will know what advantages and disadvantages, the comparison between three techniques that can be used. Okay. And the second one is that I want you to describe, to explain, not to describe, to explain about two modes of addressing. Okay, which is the first one is memory map IO, and the second one is isolated IO. Maybe for isolated IO, I don't spend much time explaining because it's actually just another development of memory map IO. So now your assignment is to explain it. So you need to read more literatures and find the information by yourself. Advantage and disadvantages comparison between these two architecture. The third one is that how interrupt-driven I/O works. Okay, which diagram I show you the change in memory and register for interrupt. Then you just need to explain the process occur, which is actually very clear. I think if you understand a little about the concept of stack pointer, about registers, program counter, then it will make sense for you. Why shown in this picture? If you have any questions, please let me know in the comment. Maybe I'll dedicate one video to explain or discuss about the problem I've given. Okay, so here inspiration for you today. Oprah Winfrey once said, having a state of mind is not something that happens to you, it's something you create. So rely on yourself, take a step forward. Don't worry, don't be afraid of failure. Because failure actually means something, it's worth it. Yeah, that's for today. Thanks for watching. I hope that this will be beneficial for you. Please subscribe to my channel, give a like, comment, and share this video to your friend.